Okay, ladies and gentlemen, dear colleagues, welcome to the inaugural lecture of Professor Dr. David Loeffler. It's in fact the first inaugural lecture of UniDistance Suisse. And I'm not going to spoil anything with regards to the CV of Professor Loeffler. That's then Professor Dr. Rolf Krause's, the Dean of the Faculty of Mathematics and Informatics job. But before I pass on the word to the Dean, I will just say a few words on inaugural lectures in general, because inaugural lectures have a very long-standing tradition at universities for new professors to introduce themselves to their academic colleagues, to introduce their field and their scientific interests to academic colleagues and also other interested people. So I'm very happy and also proud, and I think I can speak for the entire institution, for the entire UniDistance Suisse, that we are all extremely happy and proud to start this new tradition at the end of a very successful year as well. With that, I just want to mention one point. This year, for instance, we had a new record regarding bachelor-master diplomas at our diploma celebration, and it is extremely nice to continue and introduce such a tradition at the end of the year. It might seem like just a very small step tonight, but I think it's nevertheless a very big step with regards to our aim to become a cantonal university. So with that, I'd like to wish you a very pleasant and also a very interesting inaugural lecture, and I'd like to pass on the word to the Dean of the Faculty of Mathematics and Informatics, Professor Dr. Rolf Krause, to introduce our new colleague, Professor Dr. David Loeffler. Thank you.
Good evening and welcome. It's a pleasure to welcome here you as the Dean of our Faculty of Mathematics and Informatics. And as you can see, I needed to make some notes because the CV of David is so rich that I wasn't able to memorize everything. So he started to study mathematics in 2001 in Cambridge, and 4 years later he did his what is called Certificate of Advanced Studies in Mathematics, and then went to London to do a PhD at Imperial College, which is part of University of London, on what is called overconvergent algebraic automorphic forms. I know all of these words, but as you know, the meaning of a sentence depends on the context. And since I'm an applied mathematician in this particular context, I'm not sure what it means, but what I can tell you is that in 2008, when David finished his PhD, this is basically what we call the academic birth. So what you have to understand is in academia, you don't basically exist as a human being until you have a PhD. Yeah, so this is why we count, starting from the day of the PhD, people as really existing. And this happened to him in 2008. What is very remarkable, because afterwards, he was for 2 years junior research fellow in Cambridge, and then in 2010 he went to Warwick. And as you know, becoming a professor in academia is not easy because you are assistant professor, you are associate professor, you are full professor, and the English system knows a little bit more of different steps in this way. And he managed to do this, to become a professor, a full professor, in 8 years, which is remarkably fast. So usually this takes longer, and it is quite impressive that this was done in this short time. He went to Berkeley for a semester, and what I would like to note in particular is to be invited speaker on the International Congress of Mathematicians. And also, and this is something he achieved in 2021, he got an ERC consolidator grant on Shimura varieties and the BSD conjecture. It's not easy to get an ERC grant. What you have to imagine is you submit your proposal, evaluation process is two-stage. You submit your proposal, and in the very end, a success rate is significantly below 10%. Yeah, this is how it works. And it's not that the 100% who submit a proposal would be not tough competitors, right? So these are all very smart people who write very smart proposals, and winning this process is quite impressive. And we are very happy to have David here and to have him working on what is called Euler systems. And I do not know what this is. I know Euler, I know systems. Again, the context here kicks me out. As you know, I'm an applied mathematician, but from what I understood, he was giving new life to this research area. And this is something very particular. Publications, if you look into our modern scientific world, sometimes people count number of publications. Yeah? So we have, unfortunately, from my point of view, turned science into something which we try to measure quantitatively. How many publications, how much third-party funding, how many students, all this stuff gets counted, and the higher the counter, the better you are. Mathematicians are a little bit more conservative. So we look also at quality, and sometimes we even read in the papers what is written. And this happens in particular in the review process. And review process means someone reads your paper and says, excuse me, but I believe this is not good, or I believe this is very good. And there are some journals which are famous for having a very hard and competitive review process. That's Duke Mathematical Journal, and that's Annals of Mathematics. And of course, David managed to work in both. In terms of the quantitative measures we were talking about, he's doing a lot of review activities, working on editorial boards. Up to now, there were 10 PhD students and 8 postdocs as alumni from his group. And what also might be interesting, because there's also David's wife here, what also might be interesting is that much of the work done is done as a family business. Yeah, so... Yeah, so you might say, okay, this is a very traditional way of working on something, and this you also can find in research. I would like to conclude with a very final remark, because what we are going to learn is pure mathematics. And even me, as applied mathematician, sometimes I get asked, excuse me, what is it good for, what you are doing? And there's many answers to this question, and I would like to give two. The first one, you might have heard about this artificial intelligence stuff and machine learning people sometimes talk about these days. In the 80s and 90s of the last century, this was perceived as inefficient and stupid methods produced by a bunch of nerds. And somehow it has turned into something different. So one thing is, you never know what it is good for. The second is, even the quest for understanding what you do not know will give you insight, will give you knowledge. And this brings you to my final remark, and this is the eventual final most important application of mathematics, of insight, of university work. This is because we shape our mind and we improve as a society. And in that, I would like to give the word to Professor Loeffler now for his lecture.
So thank you, Nicolas and Rolf, for the introduction. I'm very, very proud to have joined the team here at UniDistance, and that it falls to me to inaugurate the series of inaugural lectures. I'm looking forward to the following lectures in this series and learning more about what my colleagues are doing. But in today's lecture, I've chosen to tell the story of one of the most famous and one of the oldest problems in my particular branch of mathematics, a problem which is disarmingly simple to state, but so challenging and so hard to answer that a very large part of the mathematics we have now was developed and grew out of the struggles of generations of mathematicians to solve this one problem. So that is the story of Fermat's last theorem, and that's the story that I'm hoping to tell today. And to start from the very earliest beginnings of mathematics and bring you to the latest research and challenges that we're working on today. So as I said, my story begins with the first attempts of human beings to do mathematics. So we don't know who was the first person to think about abstract mathematical problems. Maybe thousands of years ago, even tens of thousands of years ago, somebody arranged some rocks in a nice pattern and noticed you can put 9 rocks in a nice pattern, but 10 rocks you can't. And perhaps, we'll never know, but perhaps that was how mathematics got its start, long before the emergence of any kind of written record. What we do know is that in the earliest civilizations that we have records of, they already had some quite sophisticated mathematics. But, as Rolf mentioned, there are 2 branches of the subject, pure and applied, and the applied mathematicians were there first. So the first mathematics we know about was driven by practical everyday problems. So things like areas of shapes, dividing things between groups of people, problems with a concrete motivation. And it may have been the ancient Greeks, a little later, who were the first to study mathematics for its own sake, just purely for its own interest. And they were very interested, in particular, in the mathematics of shape, what we call geometry, particularly the kind of shapes you can draw on a flat surface, the geometry of figures in 2 dimensions. And a name that's probably familiar to a lot of you, if you've heard of Greek mathematics, is Pythagoras. So I'm sure virtually everyone here has heard of Pythagoras' theorem in school. Whether or not they remember it with fondness, I don't know. So I want to give you a little quiz question. Which of these things did the Greek mathematician Pythagoras not say? I'll give you 3 statements, and one of them is not due to him. So did he say that to eat beans is a crime equivalent to eating the souls of one's ancestors? Did he say that you must always put your sandal on your right foot first, but step into a bath with your left foot first? Or did he say that in a right-angled triangle, the square of the longest side is equal to the sum of the squares of the 2 shorter sides? So I imagine one of these statements is more familiar than any of the others. But amazingly, that's the one he did not say. There is no credible ancient source written within 500 years of Pythagoras' life that claims that he discovered this. Whereas he certainly did write and say a whole load of quite crazy things about beans. He was also strictly vegetarian, so I don't know what he did eat. But for whatever reason, a discovery about triangles has been attached to his name. And this is something that we remember him for, rightly or wrongly. And the discovery that we call Pythagoras' theorem is about right-angled triangles. So if I have a right-angled triangle, like this blue figure here, and I draw a square along each side of it, then there's a relation between their areas. As I've coloured them in here, the green area, so the area of the largest square, is the sum of the areas of the 2 smaller squares. Or to write it using symbols, as we do now, though not the way Pythagoras would have written it, we would use A, B, and C for the lengths of the sides, and then we would express this as A squared plus B squared equals C squared. So this is probably the statement that many of you remember learning in school. If you play a bit with this formula, you can calculate the length of any one of the 3 sides if you're given the other 2. And you quickly find that if 2 of the side lengths are whole numbers, usually the 3rd one will not be. So if you have the 2 shorter sides both being 1 unit, whatever unit you prefer to use, then the longer side will be the square root of 2 units. And the square root of 2, not a whole somewhere around 1.4, and so in this case, you don't get whole numbers for all 3 sides. But sometimes you do. and this was certainly known to the Greeks, that if you have a triangle with side lengths 3 and 4 for the two shorter sides, and a right angle, then the long side has length 5 units, because 3 squared plus 4 squared, 9 plus 16 is equal to 25, which is 5 squared. So there do exist some right-angled triangles in which all 3 sides have whole number lengths. And we call these, in honour of not their discoverer, Pythagorean triples. So this is a word for triples of numbers where the sum of the squares of the two smaller ones is equal to the square of the largest one. And just to finally demolish Pythagoras' claim, I wanted to show you this. So this is a clay tablet that was dug up about 100 years ago in what is now Iraq, and it was in the ruins of an ancient city dated to at least 1,000 years before Pythagoras was born. And we now know how to read these letters. This is the Sumerian writing system, and it's a table of numbers. And each row is a Pythagorean triple. So way back in the ancient Middle East, they already knew about these Pythagorean triples. And they actually must have had some quite good mathematical technology, because the largest one on this table is 1771 squared plus 2700 squared equals 3000 something squared. So too large to have been spotted just by trial and error. They must have understood some kind of pattern behind these and been able to find these large examples using some relatively sophisticated mathematics. We don't know quite how this tablet was assembled, but we can guess, because the Greeks at least managed to rediscover this, even if they didn't originally discover it. There is a recipe for these Pythagorean triples. There is a recipe you can use to cook up examples of right-angled triangles with all 3 side lengths being whole numbers. I'll give you the recipe, written in modern, very compact algebraic notation. If you take any 2 odd numbers, u and v, you can write down this formula, and it always produces a Pythagorean triple. And I've drawn here a few of the smaller examples for a few small values. And what's a little harder to show is that actually, up to scaling, up to multiplying all of the sides by some constant, any Pythagorean triple arises from this recipe. So this was all known to ancient Greek mathematicians, and is an early example of the subject that we now call number theory. And we know pretty well how much the Greeks understood and how much they didn't about number theory, thanks to this chap, Diophantus, who was one of the last significant Greek mathematicians living during the time of the late Roman Empire in Alexandria, which was at the time culturally a Greek city. And he wrote a book called the Arithmetica, which was a compendium of number theory problems and their solutions. And it was essentially summing up everything that was known in his time about this branch of mathematics. And in his honour, these questions are sometimes called Diophantine problems, illustrating the extent to which his name became synonymous with this branch of mathematics. And the recipe that I showed you a moment ago for Pythagorean triples is one particular entry of this book, Book 2, Section 8, to express a square as the sum of 2 squares. And this is something that Diophantus wrote down and which played an important role in future work on this problem, as we'll see in a moment. And before we leave the world of ancient Greek mathematics, I want to mention another problem connected with Diophantus. This is the epitaph that was written on his tombstone, composed in his honour by one of his contemporary fellow mathematicians. So here, this was originally a poem in Greek, but this is a translation into slightly old-fashioned English. Here is the story of his life, written in the shape of a mathematical problem of the kind that Diophantus himself studied. So telling you that he was 1/6 of his life he was a child, and then various other fractions of his life while he was a youth or before he got married. And if you put the numbers that you're given in this poem together into an equation, you can actually solve it and deduce how old he was at his death. So if you believe this poem, he reached the age of 84. It's a fairly respectable age for those days. And this is his life summed up in a problem of the kind he himself made famous. And rather sadly, not only was that the end of his life, but in a sense it was the end of intellectual life in Europe for quite a long time, because there was no significant mathematics, or certainly no number theory, occurring in Europe for 1,000 years after this. This was the end of mathematics in the ancient world, and it was a long, long time before our story picks up again. So that was the early history of number theory. And I want to now fast forward a bit to the problem I want to describe, Fermat's last theorem, and how it came to be formulated. So I mentioned there was this long interlude in which not very much was happening in European mathematics, but the work of the Greeks was preserved and added to by scholars in the East, in the Byzantine Empire, and later in the Arabic lands. And they preserved Diophantus's Arithmetica, for instance. And one Greek scholar in Constantinople in the year about 1400, he wrote a marginal note next to this particular item in Diophantus about expressing a square as the sum of two squares, the recipe for Pythagorean triples. And his note was possibly not such a constructive one. It was to curse Diophantus for having posed such a hard problem. Thy soul be with Satan because of the difficulty of your theorems. So around the time this was happening, Western Europe was slowly waking up from its intellectual slumber and rediscovering the scholarship and the learning of the ancient world. So this got underway maybe 1200, was happening around the time that Quatermaenos was damning Diophantus to the devil. And it was in the 16th century, I believe, that the first translations and editions of Diophantus's Arithmetica came out. And this is where the principal player in my drama enters. So Pierre de Fermat was born shortly after 1600 in southern France. He was actually a lawyer by training. He studied law at one of the French universities and worked for his whole life as a lawyer in the Parliament of Toulouse. But obviously his legal studies left him with a lot of spare time, because he's now mostly known for his contributions to science, and particularly to mathematics. And he was the first discoverer of new work in number theory since the time of the Greeks. And one of the difficulties with Fermat and his work is that he published absolutely nothing. He wrote no books. In those days, there were no mathematical journals. All we know about his work is from his letters. He wrote many letters to his contemporaries, which were preserved, and from a book that was published after his death by his son, with some of his notes and jottings and informal work. But it's a little hard to decode exactly what he was thinking and when from the incomplete record of his work that's come down to us. We do know that he had a copy of an edition of Diophantus's Arithmetica with the original Greek and a translation into Latin. And as you can see, this edition, this is the very same edition he had, has rather wide margins, enough for cursing people to the devil, but also enough for doing more constructive things with. So this particular item here is the one describing the theory of Pythagorean triples as the Greeks understood it, the same one that Quatermaenos had cursed. And he wrote a marginal note at the same point in his copy, saying something much more interesting. So remember that the problem we were discussing was to write a square number as the sum of two squares. And he said, what if we replace square numbers with cube numbers, or fourth powers, or any higher power? And he claimed it was impossible to write a cube as the sum of two cubes, or a fourth power as two fourth powers, or any higher powers than that. And then he wrote, I have discovered a truly marvellous proof of this, which this margin is too narrow to contain. Now, we know that he did have a proof for the case of fourth powers. That is one of the few pieces of Fermat's mathematical work where a complete account of the argument has been preserved. But he claimed a lot more. He was very fond of writing letters to his contemporaries saying, I can prove this, can you prove it too? Setting down challenges to his contemporaries. And a lot of these they stood as challenges long after his death, and later mathematicians tried to fill in proofs of them. So, for instance, Euler, possibly the greatest mathematician of all time, but almost certainly the greatest Swiss mathematician of all time, proved nearly 100 years after Fermat's death that the sum of two cubes cannot be a cube. But none of the generations immediately after Fermat managed to prove the full strength of what he'd written in his margin. And it seems extremely unlikely that he really did have a proof. The best guess we have is that he realized he could prove the statement for fourth powers and optimistically believed that he could do all powers in the same way. And unfortunately, it doesn't work using the methods he had at his disposal, as far as we know, but perhaps he just believed for a moment that it could be done and later realized that it couldn't, but didn't go back and cross it out in the margins of his book. I'd absolutely hate it if after my death somebody published all the jottings on the floor on scraps of paper on the floor of my study and believed that I could really do all of the things that I temporarily convinced myself I could solve. So that seems to be what happened with Fermat's last theorem. But nonetheless, the statement stood the test of time in that nobody discovered that it was wrong, and mathematicians kept on struggling, trying to prove this thing that Fermat had claimed. And they struggled for a really very long time, so this problem remained unsolved for over 3 centuries. And I want to narrate to you some of those struggles, some of the unsuccessful attempts, and how it drove the development of mathematics during that long, long period. So just to recap what the problem is that Fermat had challenged us to solve. To write it in modern notation, we want to say that if n is any whole number that's at least 3, then this equation, a to the power n plus b to the n equals c to the n, has no solutions for whole numbers a, b, and c. And Fermat himself had shown there are no solutions for if n is 4. Euler had shown that n equals 3 you can't solve, and the hope was to prove that you can't do any other values of n bigger than 3. And there's a reduction you can make. It suffices to prove that if n is a prime number, and then the general case follows, because any number will be a multiple of some prime. And so I'm going to change notation and write n equals p instead, p for prime, to remind us that it's supposed to be a prime number. So that is the problem that Fermat posed to the mathematicians who came after him. And other than Euler's discovery, not very much happened for a long while. There were many unsuccessful attempts. And one of the first non-trivial steps forward came around 1800. And this was due to Sophie Germain, who, it's a sad fact that before the 20th century, there were very, very few women who made creative contributions to mathematics. The obstacles to a woman becoming a mathematician in those days were just too numerous and too strong. So how did she manage to do this? She managed to get around the ban that existed at the time on women studying at university because of an important innovation, one that's close to our theme here and now, distance learning. So at the time, this was shortly after the French Revolution, and the École Polytechnique had been set up by Napoleon to train officers for the French army, and they offered study by correspondence. You could get all your course materials in the post, send your solutions back, and this made it much easier to hide your true identity. So Sophie Germain registered as a student under a false male name, studied under the name of Monsieur Leblanc, and was able to do a degree at the École Polytechnique. And this ruse worked very well, but unfortunately her work was too good, and the professors at the École Polytechnique insisted on this Monsieur Antoine Leblanc coming to meet them and share how he had been making all these wonderful discoveries, and she had to reveal her true identity. And the reason I'm describing her work here is because one of the things she's known for is an advance in the direction of Fermat's last theorem. So she discovered, she was able to prove that if the prime number, the power that we're looking for in the equation, if it's a prime number such that twice that prime plus 1 is also prime, so for instance, if p is 23, 2 times p plus 1 is 47, which is also prime, and we call these Sophie Germain primes in her honour. She was able to show that if p is a Sophie Germain prime, and you have a solution to Fermat's equation for that prime p, then you get some non-trivial information about the numbers in the solution. So at least one of them must be divisible by p. And this is a tiny additional piece of information, you might think, but we want to show that this x, y, and z don't exist at all. But at least we get some information about what they would have to look like if they existed, something that can tell us where we should start looking. And among the things you can deduce from this that is if there is any solution, it must be very large indeed. So this got things moving to some extent. This kick-started some successful work towards Fermat's last theorem during her lifetime and afterwards. So one of the professors at the École that she was corresponding with, Dirichlet, was able to show that there were no solutions for p equals 5, partially using her work. And a little later, there was an announcement claiming to solve the problem in general. So this chap, Gabriel Lamé, claimed to have proved Fermat's last theorem in full. And unfortunately, there was a subtle error in his work. It looked very plausible, but it relied on an assumption that turned out to be entirely false. But it was a very interesting mistake. So the mistake was analysed and explained and fully understood and by a contemporary of Lamé's called Kummer, and he developed something called the theory of ideals and ideal classes in an attempt to understand precisely how this proof had gone wrong and try and recover something from the ruins. And so this turned out to be an immensely fruitful mistake. So I'm teaching this semester an introductory course on number theory for our students here at UniDistance. And something like a third of the course is working out the theory of ideals and ideal classes, understanding all of this theory that was introduced in order to identify this mistake in a purported proof of Fermat's last theorem and understand what went wrong and how. And what Kummer was able to do with this was to prove Fermat's last theorem for, in some sense, most values of p. So he was able to, he introduced a notion of a regular prime. It's a little complicated to explain, but it's a well-defined condition on the prime p, and he showed that most primes up to 100 are regular, all except these three here. And if the prime in Fermat's equation is regular, then there are no solutions. So this is very strong progress towards showing there are no solutions at all. For these regular primes, you show that solving the equation is impossible. And pursuing this kind of line of work further, conditions you could impose on P that show there are no solutions for that P. By 1990, when the next chapter of my story starts, it had been shown that there were no solutions for P up to 4 million. So pretty good evidence for the supposition that there are no solutions at all. But of course, the primes go on forever. There are infinitely many of them. So a method that relies on you check this prime, you check this prime, you check this prime, will never prove the full strength of the theorem. But at least it can strongly confirm that the theorem really ought to be true. So this is just a sample of the methods that were tried in order to approach Fermat's last theorem. And some of the mathematical technology that grew out of this, that is now part of what we learn and use and teach to students every day, driven by the attempts of many generations of mathematicians to solve this one simple problem. So, as I said, this sort of approach, ticking off primes one at a time, can never fully solve the problem because the primes go on forever. So now I want to change the scene completely and talk about a very different kind of beast in our mathematical zoo that did eventually lead to a solution to this famous and challenging problem. So this chapter of my presentation is about things called elliptic curves and modular forms. So first, elliptic curves. These are a species of these are shapes in a two-dimensional plane described by equations of a certain specific form. So they're equations in two unknowns, x and y, for some given numbers a, b, and c. And you can write these down. You can draw graphs to illustrate what the solutions look like. There are a couple on the right-hand side of my slide here. So for different values of a, b, and c, you either get an egg shape and a curve disconnected from it, or you get one connected curve. And you get quite pretty pictures this way. And the geometry of these things is interesting and rich, but it was pretty thoroughly understood by the end of the 19th century. So people like Gauss and Kronecker and Jacobi spent all of their careers in the 19th century working on elliptic curves and elliptic functions and understood the geometry of these very thoroughly. But the arithmetic of these is much harder. So just to explain what I mean by arithmetic, it's to do with when you can find solutions when the unknowns are required to live in smaller number systems. So not just any random decimal expansion, but a whole number, or maybe a rational number, the ratio of two whole numbers. And because we're looking for much more restricted kind of solutions, they're much, much harder to find. And you can ask, are there any solutions? If there are any, how many are there? How are they distributed? And this is a very rich source of very challenging problems. So, for instance, there's a problem specifically about these elliptic curves, which I'll come back to towards the end of this talk, called the Birch and Swinnerton-Dyer conjecture, which is regarded as one of the famous open problems of contemporary mathematics. And this is a problem, as I said, about rational solutions to these specific classes of equations. And why are they relevant for Fermat? Initially, they might seem to have nothing to do with it, because the Fermat equation is not an elliptic curve. But if you assume that there is a solution to this equation for some prime p, then you can build an elliptic curve out of that solution. So you write down this formula, which is called a Frey-Hellegouarch curve, after these two chaps, Gerhard Frey at the top, and Yves Hellegouarch down here with the cello. So this is an elliptic curve which exists if and only if Fermat's last theorem is false. And what these people realized is that if it exists, it would have to have some quite strange properties. I'll say a little more about how it's strange in a moment, but the idea, the rather daring idea that these people came up with, is that maybe it's so strange that it cannot exist. that it's too weird for such an elliptic curve to appear, and hence the only possibility is that Fermat's last theorem is true after all, because then you can't write down this mysterious Frey elliptic curve, and hence this weird paradoxical object would not be there after all. So this gives maybe an approach to Fermat's last theorem. If you can prove that this elliptic curve really is too weird to exist, then the problem is solved. So various mathematicians tried different approaches to making precise this idea that the elliptic curve was too weird to exist. And the one that eventually led to a successful approach involves another concept called modularity. So there is a notion called a modular form, and I've drawn a picture of a graph of a modular form up here on my slide. This colourful little picture is one of these modular form objects. They're a little complicated to define and describe, but they're something you can draw a picture of. This is a picture of one of those. And if the shape of it looks vaguely familiar, it's possible that, for the non-mathematicians in the audience, you might be thinking of this. So this is one of the artworks of M.C. Escher, the famous illustrator and artist. And he had quite a lot of mathematical training and was very interested in using mathematical ideas to produce interesting artworks. And the way this shape of lizards fits together is the same. It has the same kind of symmetry as one of these modular forms. So this is a way you can think about modular forms, if you like, what gives rise to these lizardy pictures. And two Japanese mathematicians, Shimura and Taniyama, conjectured in the 1950s that you could match up these lizardy pictures in a one-to-one way with elliptic curves. So every elliptic curve had a corresponding modular form, and vice versa. And why is this relevant for our theme? Because if the Frey-Hellego curve exists, it cannot possibly be modular. This was proved in 1986. So modularity, the modularity conjecture of Shimura and Taniyama, implies Fermat's last theorem. You can, of course, read this in two ways. When you have two open problems, and you can show that the first one implies the second one, that might be showing that the second one was easier than you thought, or it might be showing that the first one is harder than you thought. So I think when this result that modularity of elliptic curves implied Fermat's last theorem came out, actually some people who were interested in modularity saw this as a bad thing. Maybe this proves that the modularity conjecture is too hard, because if it could be solved, it would solve this other great problem that people have been working on for hundreds of years. But history proved that they were wrong to be quite so pessimistic. So I want you to picture this scene. This is a mathematics conference in Cambridge in the summer of 1993 at the Isaac Newton Institute, which is one of these research centres where mathematicians gather to exchange their latest discoveries. And one of the speakers at this conference was this chap, Andrew Wiles. In Rolf's introduction, he mentioned that mathematicians reckon your life from the point at which you get your PhD thesis. And we also like to think of our PhD advisors as being our mathematical parents. So this chap is my mathematical great-grandfather. He was my PhD advisor's PhD advisor's PhD advisor. So he had announced a lecture at this conference on the modularity of elliptic curves. And I think this was quite an onslaught for the people present, an hour of very difficult, dense, and very strange calculations, very unlike anything that anyone in the audience had seen before. And he was claiming to be proving not the full strength of the modularity conjecture, but something that gets you a long way there. So modularity of a special kind of elliptic curves that we call semi-stable. And at the end of his allotted hour, he wrote on the board, he wrote on the board, "This proves Fermat's last theorem. I think I'll stop here." So once the applause died down, pretty much all the world's number theorists dropped what they were doing to find out what Wiles had done and how. And I can only give you the very, very vaguest hint of what he had done. But I shall do my best in this slide. His strategy involved breaking up all of the elliptic curves in nature into lots of little groups that we call congruence classes, finitely many in each group. And we want to show that they're all modular, and he wanted to do this in two steps. Firstly, you show that in each of these little groups, there is at least one elliptic curve that is modular. And this step is what we call residual modularity. So first you establish that each curve is in a congruence class that has a modular curve in it. And then you do something called modularity lifting, that shows you can sort of spread out that modularity property from one curve in each class to all the other curves in that same congruence class. And because you know there are only finitely many of them, you can count them. So we call this an R equals T theorem, because R is the letter conventionally used for the total number of elliptic curves in a congruence class. And T is the number of those that are modular. So if you can prove that R equals T, then you're done. All the curves in that class are modular. And if you can do that for all of the congruence classes, you've proved the modularity conjecture, and hence Fermat's last theorem. And this was the approach that Wiles devised and was explaining in his famous Cambridge lecture. And just to pick up on something that Rolf mentioned earlier, the key tool in the modularity lifting step, this R equals T, is what we call an Euler system. This is a very elaborate algebraic gadget whose function is to show that R is not too big. R can't be bigger than T. So, as I mentioned, all the mathematical world was reading Wiles' proof, trying to understand what he'd done. And unfortunately, one of them found a gap. There was a mistake, a gap in the Euler system argument for this modularity lifting step. And this was actually one of Andrew Wiles' colleagues at Princeton University, Nick Katz, who found a serious flaw in the construction of the Euler system that was essential for the modularity lifting. And of course, Wiles was struggling to fix his proof with the entire mathematical world watching every step. I can't begin to imagine the pressure that he was under in that time. And he was working jointly with one of his former PhD students, my grandfather, Richard Taylor, and eventually they just gave up on the Euler system approach. They decided that they couldn't make Euler systems work, and somehow they found an alternative approach. Under the glare of the attention of the whole mathematical world, they managed to find a new approach called patching and make that work instead. So they managed to repair the modularity lifting and find the full and complete proof. And that was published almost exactly a year after Wiles' initial announcement, and it finally finished this 350-year struggle by proving Fermat's last theorem and completing the challenge that Fermat had set to prove that there were no solutions to this equation. I did intend to bring a copy of Wiles' proof with me. Unfortunately, I must have left it behind when I came here to give my lecture, but it's just a small booklet, but with an incredible density of fascinating and difficult mathematics in it. It is one of the great milestones of our subject. But this is not the end of my lecture, because I want to tell you a little about what's happened in the intervening 30 years since Wiles' announcement, and to show you that although this did finally prove Fermat's last theorem, it did not close the story entirely. Any great discovery, as well as answering questions, will pose a whole load more questions. So a few of the natural questions that arose from Wiles's work. Firstly, he had only proved the modularity conjecture for semi-stable elliptic curves. And this was good enough for Fermat, but was not the full strength of the conjecture that had been advanced by Shimura and Taniyama in the 50s. And it turns out that, yes, the modularity conjecture is true in its full form, and this was proved a little after Wiles's work by his collaborator Taylor, together with these three other people, very much extending the methods from the original Taylor-Wiles proof. You could also ask, are there other equations that you can solve in the same way? So there are plenty of other extremely difficult equations you can write down that you can ask, do they have whole number solutions? And you can realistically hope that this method via Frey-Heligoarch arc curves and the modularity conjecture might solve other equations too. And perhaps disappointingly, yes, there are some other problems you can solve by this method, but not many. It's not a magic bullet that just solves every problem in number theory. It only seems to work for problems that are identifiably of the same kind, involving sums of a small number of powers, as in Fermat's problem. So the method does do other things, but it doesn't solve every Diophantine problem. On the other hand, modularity, which we saw as a step on the way to Fermat's last theorem, there are lots of generalizations of the modularity conjecture, and for these, the methods do generalize beautifully. So the patching method introduced by Taylor and Wiles has been used since then to prove many other kinds of modularity statements, and it's now a whole subfield of number theory in its own right, a large part of what we call the Langlands program, for the mathematicians in the audience who might have heard those words somewhere. So this is a very active topic of contemporary research. But it is not the topic I want to talk to you about, because I want to come back to this abandoned method in the proof, the method of Euler systems. So this is the question I want to home in on. Was the Euler system approach doomed to failure all along? Now, there do exist other Euler systems in other situations that are not useful for modularity and Fermat, but Euler systems weren't something that were cooked up out of nothing specifically in Wiles's work. They did exist in other situations. And this chap with the broad grin here, Victor Kolyvagin, was one of the people who had successfully used this method beforehand. So he made an important breakthrough towards the Birch-Swinnerton-Dyer conjecture, the problem I mentioned earlier about arithmetic of elliptic curves, using one of the first examples of an Euler system. So Euler systems do exist, just not quite in the setting where Wiles was looking for them. And you can ask what else you can do with Euler systems and whether there are other examples. And there were three examples known at the time of Wiles's work, Kolyvagin's and two others, and another one that was announced soon afterwards, although published a bit later in 2004. But somehow, after that, the field sort of ground to a halt. For a good decade, there were no more examples of Euler systems known. And I think the feeling in the community then was that maybe the Euler system method maybe Wiles was right to abandon that method because it was hopeless, these things were just too hard to work with, and there was no hope of discovering more. But it turns out that was not the case. So this was one of my first contributions in this area. In 2014, working together with Antonio Lei and with my wife Sarah, we managed to discover the first new Euler system to come along for this after this decade-long wait. So here's a picture of the three of us, me with rather less grey hair than I have now, taken at the conference for Glenn Stevens' 60th birthday in 2014. So this was one of the conferences where we announced the discovery of our new Euler system. And just to give an idea how we were able to find this new object, which people had struggled to find for so long, there's a number you can attach to an Euler system called its rank. I don't want to get into exactly how it's defined. It's it measures something about the shape of the Euler system. And the four classical Euler systems, the ones that I described, the three that were known in Wiles' time and then the one that came soon after, they're all rank 1 Euler systems. And there was a conjecture that if you wanted to discover more Euler systems beyond that, you needed to look at higher ranks. So it was believed that any further Euler systems except those four must have rank at least 2. But this was wrong. So we found another rank 1 Euler system in a situation where these conjectures predicted that a rank 2 Euler system should exist. We think the conjectures were right. The rank 2 Euler system is there, but we can't prove that. But we can prove that this other lower rank Euler system exists as well, and that is good enough for the applications you want. And this sort of got the subject moving again. So the methods that we used have led to many more Euler systems. All of rank 1, but rank 1 is still enough to be for the applications of Euler systems. So I'm just going to give a few references. These are the research announcements in which some of these new Euler systems were discovered. And you can see that after our first discovery in 2014, these started to come quite quickly. So this last one on the list, this is two PhD students at the time of their work using the methods we'd introduced, and they actually discovered a whole infinite family of Euler systems. So from this 10-year struggle to find any more examples, suddenly we had a factory churning out new examples as a regular production line. And these have been used to do all kinds of interesting and exciting things. So to push back the frontiers towards the Birch-Vinton and Dyer conjecture. We haven't proved the whole of the conjecture yet, but we've at least made some measurable progress towards it and to other related conjectures and generalizations. And there are enough problems in this area and enough accessible topics for research to keep a whole research group busy. In fact, many research groups. So this is what I do. I'm focusing in my research on the construction and study of Euler systems, and I have a whole team, several of whom are here with us today, who are all carrying out research on the study of Euler systems. So here are a few of the faces from my research team. There are a few who I left off this collage because I couldn't find photos of them at short notice. But these are a few of the people who are working with me or have recently been working with me on the theory of Euler systems. So some of these were part of my team in Warwick and remained behind in Warwick when I moved here. Some are working with me here at UniDistance. I'm gradually building up a new research team, but these people are all working on problems in number theory with Euler systems as the common theme. So where before this was a subject that was stuck and was making no progress in 10 years, now we have enough accessible and exciting problems to keep a whole team busy churning out new discoveries and new research. And I just want to conclude with one current project we're working on right at this moment, which is to revisit Wiles' approach to Fermat's last theorem, the first approach via Euler systems. So I'm afraid I'm going to direct this to the mathematicians in the audience. What we need is an Euler system of a certain particular kind, an Euler system for the adjoint of an elliptic curve. And you can look for this in multiple places. Oh, sorry, I should mention that there were two groups working on this. We're working on this, and there is a second research group in the US who are also in the process of constructing an Euler system in this setting. So where for quite a while there has been no discovery of an Euler system here. Suddenly two are coming along at once. But anyway, the new ingredient is, rather than looking in the most obvious place for this thing, so in the product of two copies of the modular elliptic curve, we use an alternative widget called the Hilbert modular surface. And this bypasses the problem which screwed up Wiles's approach to Fermat's last theorem, which is what we call the trivial zero problem. And you can evade this trivial zero, which destroyed Wiles's original approach, by using this alternate construction of Euler systems via Hilbert modular surfaces. So we think it's really interesting to revisit this approach, which at the time was unsuccessful, and to see if we can redeem it to show that Euler systems could have been used, maybe, to prove Fermat's last theorem. And we can't yet give a new proof of Fermat's last theorem. Maybe ask me again in a year or two's time. I still have hopes that we can give a new proof independent of the patching method that was used instead. But we can use this new Euler system to do other things, such as the Iwasawa main conjecture for the adjoint motive of an elliptic curve. And that's just a few of the interesting projects that are going on here at UniDistance in number theory with Euler systems as a theme. And so I've taken you from the very earliest beginnings of mathematics, the prehistory of the subject, up to contemporary research problems. And I hope you've enjoyed the talk. Thank you.
Thank you very much. I have the pleasure to ask the audience for questions. And as we work at a distance with slightly more modern techniques, we have online questions and we have questions from the people here in the audience. I have the oldest question before we go ahead with questions from the audience, which was posed 21 minutes ago.
See?
Now we have to figure out to which slide it would belong. And it says, by exist, you mean that there are no integer rational solutions on that curve or no solutions at all? So if you know which slide it was, then...
I'm guessing this refers to this slide. So on any elliptic curve, there will be many points with real coordinates. The set of real number solutions is always non-empty and always infinite. So the problem which is challenging is to find out whether there are solutions of this much more restricted kind, in which the unknowns, the x and y we're trying to solve for, are both rational or integral numbers. So that's the challenge that we have to face. Showing that there are solutions at all is not difficult in this case. It's showing that there are this special kind of integer or rational solutions. So I hope I've correctly deduced what the question was in that case.
Many thanks. So that was our first online question. Do we have questions here in the audience? If not, we have more online questions, and you can think about your questions while the online ones are answered. And the second one says, are there similar results for more than two terms on the left-hand side? For example, a to the power of p plus b to the power of p r plus c to the power of p equals d to the power of p.
There are similar results, but when you are adding together more terms, then it becomes easier to find solutions because you have obviously more possibilities you can try. So at one point it was conjectured that you couldn't have fewer than n nth powers adding up to an nth power, and that is consistent with Fermat's last theorem, but would be massively stronger. But that was actually shown to be false. So I think there's an example with 3 fourth powers adding up to a fourth power, if my memory serves. And this was discovered, I think, in the late 80s or early 90s. And there's actually an interesting and possibly rather cruel connection to what I was describing in my talk. So during this period, well, I should say that this example of 3 fourth powers adding up to a fourth power, if I remembered correctly what the example was due to a mathematician called Noam Elkies. And during the year when Wiles and Taylor were desperately trying to fix the proof of Fermat's last theorem, there was an April Fool's Day joke circulated on the mathematical email lists that many mathematicians were subscribed to, claiming that this guy, Noam Elkies, had found a counterexample to Fermat's last theorem, so the theorem was false all along. But in fact, this was just an April Fool's joke, but I think it was a particularly cruel trick to play on somebody who was trying their hardest to fix and correct one of their work on possibly the oldest and most famous problem in mathematics, to joke about it all being wrong because of this purported counterexample. But yes, so there do exist examples of sums of nth powers adding up to another nth power if you allow more than 2 terms.
Who busted the joke? Do we know who busted the joke?
There are various theories. I've heard it ascribed to several people, but I think I shouldn't cast aspersions here.
It's said in Simon Singh's book, actually, but I don't remember. I have a question. What happened to Sophie Germain after it turned out that she wasn't Antoine Leblanc? I mean, was she allowed to continue her mathematical career?
She was allowed to continue studying, but they refused to actually give her a formal degree.
What?
Apparently, Gauss nominated her for an honorary degree from Göttingen. But unfortunately, she died before the degree could be conferred. She died very young. She was in her early 30s, I think.
Do we have additional questions here from the audience?
Is any research being done on finding Euler systems with a rank higher than 1?
Yes, a great deal of research is being done, and there have been approaches proposed, and unfortunately it does seem to be a difficult problem. There is one setting which I have worked on where you can construct an Euler system of rank bigger than 1, but unfortunately the argument is rather disappointing. You construct an Euler system of rank 1 in that situation, you use it to analyze in very, very great detail the arithmetic of the situation, the Galois representation you're studying, and then somehow you deduce at the end of this long analysis that actually there was a rank 2 Euler system there all along. But somehow, in order to get there, you have to solve all of the problems that you would be wanting to use Euler systems to solve. So it's a sort of consistency check, but it isn't useful as a tool by that point. There are other research groups who are working very hard on trying to build these higher rank Euler systems, but with mixed success so far.
So then we go to the next online question, which is, what do you enjoy most about doing mathematics?
Well, something I personally love about working in my subject is how little machinery, how little baggage there is in order to creatively do mathematics. You can think about and work on mathematical problems wherever you are, whatever you're doing. Maybe if you're waiting for a bus at a bus stop, you can pull a notepad out of your pocket and do some calculations. You don't need a huge laboratory. You don't need a massive team in order to make any progress. Of course, if you have a massive team, you can make progress faster. But an individual mathematician can make discoveries on their own and without needing huge amounts of machinery and backup. So it's something where the problems are very simple and you can just hold them in your head and struggle with them on your own wherever you happen to be and whatever you happen to be doing. In a sense, it's almost a way of life rather than just a job, being a mathematician, because the research follows with you wherever you go.
Any additional questions from the audience? Because online is active. So we will see. Are there or could there be any other known areas, maybe even outside number theory, where elliptic curves or Euler systems could be applied to find solutions or proofs?
Well, elliptic curves certainly have applications outside number theory. So one of the most celebrated kind of contact points between number theory and applied mathematics of use in the real world comes via cryptography, so sending secret messages. And this is something that my students are learning about in the course I'm teaching this semester. So I don't know if any of you have remember the time when you used to install software on your computer and you would actually go and buy a CD rather than just downloading something off the internet. And you would put your CD or maybe even your floppy disk in your computer, and then you would have to enter some random string of numbers and letters that was your license key, proving that you actually owned that software. And the way those license keys are encoded and the way that they check that you have the correct key actually uses elliptic curves. So one of my research co-authors, a guy called Dimitar Djechev, used to work for Microsoft, and that was his contribution. He did the license key encoding for a particular issue of Windows using elliptic curves as a summer job when he was a postdoc. So yes, you can use elliptic curves in the real world, and cryptography is one of the principal uses of them. As for Euler systems, that's maybe a tougher ask. They're a very, very specialized tool for solving these particular kinds of theoretical problems in number theory, and I'm not sure would be willing to claim that they're something that you encounter in other areas outside number theory. But within their domain of number theory, they're an extremely powerful weapon.
Okay, so then, a question from the audience. Great.
It's a completely ignorant question, excuse me, but if I were to go home tonight and talk to my mother and say, I saw this wonderful seminar about number theory, I don't know what it means to say number theory. How can you explain that in very common terms, what it means about that? I know what numbers are, but I don't know what number theory is.
Well, you could maybe motivate number theory for your family with some of these examples from very early on in the history of the subject. So square numbers, triangular numbers, putting a certain number of objects into a nice pattern, into a nice shape. And you can do that with some numbers and not with others. So here I've got 9 things put in a square, and I've got 6 things put in a triangle. And that's an idea which is fairly easy to communicate, I would hope. And then you can ask, is there any number of objects which can be put into a square and also into a triangle? Same number of objects that you can arrange in both of these shapes. And that's a number theory question. And it's one which has a rich and interesting solution. But just to explain the question, I think is something that could be explained to anyone who has ever tried to count things.
Okay, so then we go to the last question of the evening, which was posted online. There are so many questions. I'm afraid.
The questions are coming in steadily.
We define this to be the last question. And
David can then sit there and reply.
And can reply, right. I think that's a very good idea. So we will go and have a drink and David can answer questions. So the question is, do you believe the ABC conjecture has been proved?
That's a good question.
Maybe you could shortly elaborate on the ABC conjecture.
Someone in Japan.
So the ABC conjecture, which one of my UniDistance colleagues has raised as an online question here, is a more general conjecture that would have important implications for Fermat's last theorem. So it shows that for a much more general class of equations involving adding together two smaller integers to get a larger one, that you get some relation between the prime factorizations of the things you're adding together and of their sum. And it's relevant to Fermat's last theorem because if the ABC conjecture is true, that it implies that there are most finitely many solutions to Fermat's equation across all values of P. Of course, we now know there aren't any at all, thanks to Wiles and Taylor, but this conjecture is a great deal more general. And it's somewhat a topic of controversy in the mathematical community, because a Japanese mathematician named Mochizuki has proposed a solution to it, but his solution adds up to, I think, several thousand pages of very, very dense mathematics, which it seems only he understands. A number of people have tried very, very hard to understand this alleged solution and come away disappointed. So this is really a bit of a challenge to the way we do mathematics. If a solution to one of these open problems is proposed, it's sort of expected that the mathematical community should work together to determine whether the solution is correct or not. But when the solution is enormously complicated, sometimes people just give up and say, we really don't know whether this is correct mathematics or not.
But also gaps were found, right?
Well, the issue is that Mochizuki denies that they are gaps. And who do you believe? So I could have given another lecture on a rather different theme, which was about whether you can check the correctness of a mathematical proof using a computer. And this would be a way of getting the human beings checking mathematical discoveries out of the loop and getting some kind of unbiased and authoritative answer as to whether new mathematical discoveries were correct or not. Unfortunately, no one has done that for the ABC conjecture yet. I'll go out on a limb and say that I rather suspect that the solution is incorrect, but that's a suspicion. I'm not saying I can prove it to be wrong. But it is sort of an unfortunate situation that we have one of our major open problems which might or might not be solved, and it's hard for the mathematical community to be sure at the moment.
As we do, and as is good tradition on our conferences, at a certain point if the discussion becomes deep, we always decide to continue it with a drink in our hands. And I would like to thank David very much again indeed for his wonderful lecture. Thank you. I would like to apologize for the last two online questions for not being answered. Please feel free to have a drink with us or to get answer in a different way. And I wish everybody a pleasant evening.
Well, thank you all for coming, and I hope you enjoyed the lecture.
Just a second, please. We have a present.
Oh, wonderful.
That is a surprise.
Thank you so much.